The objective today is to explain what the Intel manual says about fundamental data types, and look at that, we're already on chapter 4. And for anyone curious, I found that when I am writing using this Surface book, when I'm writing on a PDF, as you can see here, we're on page 87. After a while, that thing starts to slowly crawl. So what I've been doing is just resaving these PDFs with brand new like writing marks here. And along the way, I must have downloaded a different volume, even though it looks like the majority of things are the same in each of the different versions of these Intel manual volumes. The point of me telling you this is if you're following along and looking at the page numbers here, well, on the last one, we're actually on page 89, so it looks like this newest version I have is a little bit shorter, and I'm still trying to discover what exactly is missing or what's been added to these different versions. So we'll skip this first paragraph. It's pretty worthless because I'm going to just get into it. Chapter 4 begins by saying the fundamental data types are bytes, words, double words, quad words, and double quad words. So that's your first question. What are the 5 fundamental types? And it'll say refer to figure 4-1. Take a look at that in a second. The first thing is very easy. A byte is 8 bits. Okay. A word is 2 bytes, so a word is 16 bits. Then a double word is 32, quad word is 64, and so on. I've rarely seen anything that's a double quad word, though. I mean, it wouldn't exist if there wasn't a need for it, so double quad word is kind of a mouthful to say as well. You know, if I was designing this processor from the ground up, maybe I would just say word 16 or word 32, just to make it very clear how many bits you're working with at any given time. But I'm not in the chip making business, I'm in the education business, so here we go. A subset of the IA32 architecture instructions operates on these fundamental data types without any additional operand typing. So if you have yourself an operand or a value, that value is going to go into one of these data types, be it a byte, a word, and we can look at a high byte of a word or a low byte of a word. If you have a double word, we can look at the high end or the low end of that as well. And notice here the n. Computer science people love to use n as a variable placeholder there. So you have n all the way down. Everything has at least 1 byte in it, but you're going to add another byte for your word. And then down here, your word is going to add another 2 bytes. So let's get down here though and read that the quad word data type was introduced into the IA32 architecture in the Intel 486 processor. So I put AKA the 8486. This is in 1989. And then the double quad word data type was introduced in the Pentium 3. So that's the 8th generation of the x86 architecture here. So it's introduced in the Pentium 3 processor with the SE extensions, SSE I mean, and what that stands for is Streaming SIMD extensions. You can do more research on that, or maybe I can make a video on that later. Now figure 4.2, I'll do a complete separate video on that because it's pretty complex, but it says that that figure shows the byte order of each of the fundamental data types when referenced as operands in memory, and the low byte, that is bits 0 through 7, of each data type occupies the lowest address in memory, and that address is also the address of the operand. So it'll be helpful for you to remember that Intel is going with this lowest address first. Here's the diagram just because I want you to be able to see it for now, but again, a whole separate video, it'll be part 22, and I'll really dig in deeply because this took me a while to digest. Alright, so let's talk about the alignment of words, double words, and quad words, and quad words. So we're talking a 16-bit data type, a 32-bit, 64, and what these do not need, they do not need to be aligned in memory on natural boundaries. That's a really good sentence right there because that's the confusion I had when I was looking at this. So here's your question, and I'm going to be a little funny in this. Do data types need to respect natural boundaries? The professional way to look at it is it does not need to be aligned, but I like understand the human need for natural boundaries or respecting natural boundaries, so I use that terminology right there. Now it says the natural boundaries for words, double words, and quad words are even numbered addresses. Addresses evenly divisible by 4 and addresses evenly divisible by 8, respectively. However, to improve the performance of programs, data structures, especially stacks, should be aligned on natural boundaries whenever possible. So this diagram is going to confuse us when we dig into it. For now, know that we actually should be respecting these natural boundaries. So I'll just ask, why should natural boundaries be used? And the sentence immediately says, to improve the performance of programs. Now the reason for this is that the processor requires 2 memory accesses to make an unaligned memory access. Aligned accesses require only 1 memory access. So to really digest that sentence, you should understand that a single access is a single moment in time. And that's the whole hertz thing. I think I have a great video on how to understand hertz, gigahertz, well, megahertz to start with. But computers can only do one thing at a single instance in time. So with that said, it makes sense to go ahead and separate these. You might feel like it's a waste of space, but you don't want this overlapping to occur. And I just can't help myself. Let me show you that part in the diagram. So if a double quad word exists right here at address 0, you can see by the arrow it goes all the way up. So that double quad word has these values in it. I can't even highlight appropriately. So here's the values, here's the address. If I need the computer to access a word that starts at address 1 right here, well, it'd be accessing this within the double quad word already, and then that's the confusing bad part that the Intel manual is warning us against. Alright, so a word or double word operand that crosses a 4-byte boundary or a quad word operand that crosses an 8-byte boundary is considered unaligned and requires 2 separate memory bus cycles for access. That is exactly what I was saying about the Hertz idea. Hertz is a measure of cycles. Well, some instructions that operate on double quad words require memory operands to be aligned on a natural boundary. These instructions generate a general protection exception if an unaligned operand is specified. So a natural boundary for a double quad word is any address evenly divisible by 16. Other instructions that operate on double quad words permit unaligned access, and this is without generating a general protection exception. However, additional memory bus cycles are required to access unaligned data for the memory. So the question is, when will a general protection exception occur? And here's another question for you at the end of the paragraph. What happens when the memory bus needs to access unaligned data? The answer is the memory bus will need to use additional cycles to do so. So the summary for this entire set of paragraphs is all about the alignment of data. And as I look at my notes from before, I could turn this one into a question too. And the answer is 2 separate memory bus cycles will be required. Alright, and to finish today's video, let's go ahead and read quickly about numeric data types. Although bytes, words, and quad words are fundamental data types, some instructions support additional interpretations of these data types to allow operations to be performed on numeric data types. That is to say, signed and unsigned and floating point numbers. When you have single precision floating point numbers, that means you have 32 bits in a single precision floating point. Single precision and double precision data types are supported across all generations of SSE extensions and Intel's AVX extensions. The big takeaway I want you to have right here, and we're going to end here even though it says look at the diagram, we'll look at that next time, but the big takeaway right here is I just want you to know there are 2 examples of numeric data types, signed and floating point. And I could talk about that a little bit more in the video after the next one. In the next video, part 22, I'll go ahead and break this diagram down even further than I did today.